One of the greatest challenges is figuring out how to take the humans and fly them safely through the atmosphere down to the surface.
The air is so thin on Mars that the vehicles don't slow down to a point where you can light your engines below the speed of sound. That's a big problem, and how we might solve that is to use very large, potentially very large heat shields or aeroshells, things that actually use the air pushes on to slow down.
Any concept that we propose should be capable of doing aero capture maneuver first, and then doing the entry, descent, landing part. The problem,
the shape that we want to slow us down at Mars is exactly the shape that we don't want when we're fighting to leave Earth. So we need to transform in some way. When we transform also makes a difference. This mission is a complex choreography of a number of vehicles leaving for Mars at different times, and we want the maximum reliability and crew survivability out of that entire complex
during launch. Our concept, we call that as Transformable Entry System Technology, is very much like an umbrella. Think of an umbrella structure that conforms to the launch shroud. It's made up of skin and bones, skin being TPS, and bones being the structure. Once launched, this configuration can be transformed into a very large aeroshell surface. And this gives us a very low ballistic coefficient for entry at Mars. There's also other transformations built into the test concept. The second transformation is really this movable surface that allows us to orient the lift vector during entry any way we want. The third transformation is, think of an inverted umbrella. When you invert the structure, it forms a landing system. In the next few minutes, you'll hear a lot more details of this concept.
When you deploy a large flexible drag device in a turbulent flow environment, you have to be concerned about dynamic oscillations. The test architecture, since it uses rigid support, can be designed to mitigate these oscillations.
Finite element model was very well optimized using hypersizer. Most of our margins are down to 0.5 and 0.25. so that we know that we have very high fidelity on our mass estimates.
The intent of analysis, which is what I do, is to determine using modern computational fluid dynamics tools what the heating and pressure loads and shear loads are going to be on the surface.
The concept of the carbon cloth as a decelerator is not new. For this application, the advantages are that you can basically deploy it and you need a flexible material. The primary design issue for the carbon cloth is A, is there going to be flow through it, and B, how much recession will it experience both in aero capture and in entry from orbit.
For the test setup, we're actually testing several different materials. We're going to be testing a 3D carbon weave, and then we're also going to measure the plain carbon weave, which is just a plain weave.
The test concept has actually three heat shielding components. The central disc here is covered with a conventional thermal protection system like Apollo or Mars Science Laboratory, and it is detached prior to turn on the retro rocket engine. The outer part is the carbon cloth that was described earlier, and the function of the carbon cloth is really great because it can re-radiate back to space heat coming on board both from the front side and the back side. We've developed a flexible TPS, and there are two varieties of this. One is similar to the Pica impregnated carbon ablator Pica, and the other one similar to the silicone impregnated reusable ceramic ablator. And this makes that element of the total TPS system much lighter.
This quick study gives us confidence in the basic decelerator performance, and we're convinced it's worthy of serious continued effort. We recognize the need for work on reliability, but we've already noticed a nice feature that much of it can be done on the ground, and certainly all of it can be done subscale, exploiting structural similitude. The critical operations don't need combined load environments. We don't need thermal and mechanical loads at the same time. So we can do very relevant flight testing at Earth and at subscale. This means the development is manageable and achievable.
Programs like TEST are especially important to educational institutions. From my perspective, they not only provide a test bed for innovation, but are also a vehicle to motivate a new generation of scientists and engineers in our educational pipeline.
The team is very excited and look forward to further developing this concept in the near future, not only for Mars, but also for other destinations. And I want to thank you for taking time to come to know our concept we call TEST.
I didn't know. I broke everything new again, everything that I'd owned. I threw it out the windows, came along. Extreme waves I know will part the colors of my sea. Perfect color me. Extreme waves that helped me out late at night. Extreme places I had gone, but never seen any.